everyone, my name is Monica. We're happy to have you with us for getting started with the basics of IP. In this series of videos, we will be moving step by step to help you gain a systematic understanding of all aspects of the field of data communications, including data networks, switching, security, routing, reliability, BGP, and multicast. Now let's get started.
In this training session, we talk about TCP IP basics. You will understand the data exchange process, understand the TCP IP reference model and its basic concepts. The TCP IP model is the basis of the entire network. This model was proposed earlier than the 7-layer OSI reference model. As shown in the figure, the TCP, IP, and OSI reference models correspond to each other. The OSI model's upper 3 layers, transport layer and network layer, are mapped to the TCP IP model's application, host-to-host, and Internet layers, respectively. In the TCP IP model, the data link layer and the physical layer are combined into the so-called network access layer. TCP IP protocol suite. TCP IP stands for Transmission Control Protocol, Internet Protocol. The TCP IP protocol suite contains multiple protocols. These protocols work together to make the entire Internet run properly. Here we talk about 2 typical protocols, TCP and IP. This diagram shows the layers and their functions in the TCP IP reference model. This slide describes the protocols that are working at each layer of the TCP IP reference model. The application layer has some protocols to be highlighted. HTTP stands for Hypertext Transfer Protocol and its port number is 80. Telnet is a simulated remote logging protocol and uses TCP port 23. The File Transfer Protocol, abbreviated as FTP, is used to transfer files. TFTP is the Simple File Transfer Protocol and can be used in the system upgrade. There are 2 typical protocols running at the host-to-host layer. One is TCP, which stands for Transmission Control Protocol. TCP transmission is reliable. The other is UDP, or User Datagram Protocol. Unlike TCP, UDP implements best effort traffic forwarding. Every application layer protocol selects its own host-to-host layer protocol that best satisfies requirements. For example, if the application layer requires a reliable session, TCP is selected. TCP provides connection-oriented services. UDP provides connectionless best effort transmission. TCP requires that each data packet be reliably transmitted, such as data for HTTP web browsers, email programs, and file transfer programs. UDP merely sends data packets and does not care about whether a next hop receives the data packet. For example, IP voice and video stream data is transmitted using UDP. TCP packet format. In the picture, the data field carries upper layer data, and the TCP packet header is attached before the data field. The source port field is a source port number, and the destination port field is a destination port number. A port number is an integer ranging from 0 to 65535. Port 0 through 1023 are reserved. These port numbers are reserved for some known applications. For example, port 80 is reserved for HTTP protocol. Port numbers greater than 1024 are reserved for user-defined applications For example, a process starts a local port 2020. Once data arrives at port 2020, this port sends data to the application. If packets carry 10.1.1.1:80 to access a server, packets access TCP port 80 assigned to the IP address. When the domain name is entered on the browser, but no port number is entered, the program uses a default port number for a specific application. For instance, the default HTTP port number is 80. The sequence number field is a sequence number of a packet. The acknowledgement number field is used to confirm that a packet is received. These two fields are used to ensure the reliability in transmission. The control bit field is 6 bits long. Each bit stands for a special purpose if the bit is set to 1. A UDP packet is simpler than the TCP packet. The UDP packet merely contains 4 fields: source port, destination port, length, and checksum. UDP transmits lower layer packets in a reliable fashion because UDP packets carry no sequence number or acknowledge number. TCP connection establishment. A TCP session must be established before any TCP-based application transmits data. The data is transmitted over the session. As shown in the figure, device B is a server, and device A is a client. Device A and device B are to establish a session, and device A initiates a TCP connection to device B. 3 fields are involved in this process: sequence number, acknowledge number, and control bit. First, device A sends device B a TCP message with a sequence number of 0. Upon receipt, device B replies with a message carrying a valid acknowledge number. The control bit field contains an important bit called synchronization. In data with a sequence number of 0, the synchronization bit is set to 1. The TCP message sent by device A also includes other information, such as a destination port number and a source port number. When device B confirms that the port to be accessed by device A can be opened, device B replies with a TCP message to device A. In this message, the acknowledgement field is set to 1. This message is used to confirm the message with sequence number 0 sent by device A and request device A to send a next TCP message with sequence number 1. In this message sent to device A, the synchronization and acknowledgement bits are set to 1. Upon receipt of the message, device A replies with another TCP message to device B. In this message, the sequence number is set to 1, and acknowledgement bit is set to 1. The three-way handshake is complete, and a TCP connection is established. The teardown of a TCP connection is more complex and involves the four-way handshake. Device A and device B exchange data over the TCP connection. Before choosing the connection, device A sends a TCP message with a FIM bit set to 1. Upon receipt of the message, device B replies with a TCP message with an acknowledgement number to device A to confirm the received message and send another TCP message carrying the FIN and acknowledgement numbers to instruct device A to close the connection. Upon receipt of the messages, device A relies with a TCP message carrying the acknowledgement number to device B to confirm the disconnection. TCP sliding window mechanism. Device B has 3 units of empty buffers. During the three-way handshake for TCP connection establishment, device B notifies device A of a wing field of 3. This value indicates that 3 units of buffer are empty on device B, and device A is able to send a maximum of 3 messages to device B at a time. Device B sends an acknowledgement message to device A after receiving all the 3 messages, instead of sending one for each message. After the three-way handshake is complete, device A sends 3 messages with sequence numbers of 101, 102, and 103 respectively. After receiving them, device B fills these messages in the buffer. The buffer is now full of data. One piece of data is obtained by the CPU for processing. Device B sends device A an acknowledgement message to confirm the last received message with sequence number 103. The acknowledgement message carries the acknowledgement field of 104 and the wing field of 1. Value 1 indicates that device B has a single buffer unit available. Next, let's move on to the Internet layer. The Internet layer provides various functions. This slide describes some of them. IP packet format. The data field carries upper layer data. The other parts belong to the IP header. In the following example, IPv4 is used. The version field is the IP packet version number. The 4-bit header length field is the size of the IP header. The 8-bit priority and type field is used to implement QoS functions. The 16-bit total length field is the total size of an IP packet. The 16-bit identification field and 13-bit fragment offset field are used in fragmentation. The flags field is used for special purposes. The time to leave field is a TTL value used to prevent loops. Each time an IP packet passes through a router, the TTL value describes by 1. When the TTL value becomes 0 on the router at the last hop, the packet is dropped. The last router replies with an ICMP message to the source and informs the source that the packet is dropped. The 8-bit protocol field notifies the receive and the end of type of packet carries in the data field. The 6-bit header checksum field is used to determine whether an error occurs during data transmission. The 32-bit source IP address and destination IP address fields are the source and destination IP addresses, respectively. The Address Resolution Protocol ARP generates mapping between IP and MAC addresses of devices and saved mappings in ARP entries. ARP runs at the bottom layer of the entire IPv4 network. ARP has some drawbacks. First, it broadcasts packets to find a MAC address mapped to a specified IP address. Broadcasting burdens a network. Second, ARP is unreliable. As shown in the figure, when PC1 requests for the MAC addresses of PC2, PC1 sends a broadcast ARP request. In this request, the source MAC address is set to PC1's MAC address, and the destination MAC address is set to all Fs, indicating that it is a broadcast frame. The sender's IP address is sent to PC1's IP address, and the destination IP address is set to PC2's IP address. After PC2 receives the ARP message, PC2 replies with an ARP message to PC1. PC1 constructs an entry for the mapping between the IP and the MAC addresses of PC2. The receive end of the ARP messages does not need to send an acknowledgement message to the transmit end. PC1's gateway is PC2.168.1.254. When PC1 accesses the Internet through a router, PC2 sends an ARP message to PC1. In this message, the source IP address is set to the router's IP address, and the source MAC address is set to PC2's MAC address. Upon receipt of the false message, PC1 maps the router's IP address to PC2's MAC address and saves the mapping as an ARP entry. In this case, PC1 sends frames to PC2 instead of the gateway. PC2 runs software to obtain and analyze packet header information sent by PC1. As a result, PC1 information is leaked. This is ARP spoofing. Internet layer related tools. Ping is used to monitor reachability of a link from a local node to a remote address. Ping runs over ICMP. The table describes the IP and MAC addresses of each node along the path. The process of the PC accessing the web server will be explained later. A data packet is sent in the top-to-bottom manner on the PC. A header is added to the packet through each layer. The packet becomes a bit stream at the physical layer. After the bit stream arrives at the router checks whether the frame header matches the router's MAC address. If a match is found, the router forwards the packet to the next hop. The packet ultimately reaches the server. The PC constructs a data frame for an HTTP process. Data is forwarded to the server. The HTTP process is developed based on TCP. A TCP header is added to data before the data reaches the transport layer. In the TCP header, a source port is randomly generated, and the destination port number is set to the port number to which the remote server is listening. When the data arrives at the Internet layer, an IP header is added to the data frame. In the IP header, a source IP address and a destination IP address are set. A protocol number of 6 indicates that the TCP header follows the IP header. After the packet arrives at the data link layer, an Ethernet header is encapsulated into the packet. The source and destination MAC addresses are set in the Ethernet header. The IP header is used only in logical path transmission, and the MAC address is responsible for physical addressing. The MAC addresses are used only on the Ethernet network. The source MAC address is set to the NIC's MAC address on the PC, and the destination MAC address is set to the gateway's MAC address. The packet is converted into a bit stream and sent to R1. Upon receipt of the bit stream, R1 restores it as a frame and checks for the frame header. R1 finds that the destination MAC address is a local MAC address and removes the frame header. It also finds that type in the frame header is IPv4 and possesses the packet using the IPv4 protocol stack. R1 finds the destination IP address is not a local IP address and searches the routing table for a matching next hop, which is R2. R1 adds another Ethernet frame header to the packet. In the frame, the source MAC address is set to R1, G001's MAC address, and the destination IP address is set to R2, G00's MAC address. After receiving the frame, R2 finds the destination MAC address is a local MAC address and removes the frame header. R2 uses the IPv4 protocol stack to process the packet and finds that the destination IP address belongs to a direct network segment but is not a local one. R2 adds another frame header to the data and sends it to the server. After receiving the data frame, the server checks the frame header and finds the destination is its own MAC address. The server removes the frame header and processes the remaining data using the IP protocol stack. The server finds that the destination IP address is a local IP address and removes the IP header. The protocol number field reads 6, indicating that a TCP header follows the IP header. The server then possesses the remaining data using the TCP protocol stack. The server finds the destination port number of 80 in the TCP header, removes the TCP header, and sends data to the HTTP process.